Good morning. Today, I'd like to talk about local flatness, and finally, we're going to see the connection between all of this stuff we've been talking about and gravity. Firstly, I want to think about just curved surfaces in ordinary geometry. I'm going to think about such a surface with some particular point P located within that surface. I'll think of having coordinates on the surface. P has some coordinate values for this coordinate system, and I'm going to imagine looking at the piece of the surface close to P. I'm going to think of having such a small piece of the surface that it looks flat to me. Even so, it's not necessarily true that the coordinates are flat coordinates. I could imagine taking an even smaller piece of the surface containing P so that the coordinate curves begin to look like parallel straight lines. Once I see that, I see that close to point P, there will be a coordinate system that looks like a flat coordinate system. I could do some coordinate transformations here to make the coordinate axes at right angles to each other and have, at least locally, at least close to point P, a coordinate system that looked Cartesian. When I want to do tensor operations at point P, I will pretend that the space is entirely flat as long as I only think about point P and points that are close to point P. In a certain sense, we are approximating the surface by the tangent plane there. We have already observed that if we try to simulate gravity with, say, a rotating space station, then this will mess up the synchronization of clocks and disturb the whole idea of an inertial reference frame. If I want to do in special relativity what we do for these surfaces, somehow we need to have a way of, at least locally, getting rid of gravity. You can imagine Albert Einstein saying, "I've just had the most wonderful idea. Locally, I know how to do a coordinate transformation that gets completely rid of gravity." And you tell him, "Well, Einstein, that's a very big claim. Can you prove it?" Einstein says, "Yes, I have two proofs. One of them is very complicated and mathematical. The other one is more obvious and physical." So the person says, "Well, show me that second one." Einstein takes him up to the top of a tall building. The fellow says, "Why are we up here, Einstein?" And he says, "Well, I want to show you physically how I can locally get rid of gravity, but I have to warn you, you're not going to like it." The fellow says, "Well, go on and show me." So Einstein pushes the fellow off the top of the building and he falls. As he's falling, he's yelling at Einstein, "Are you crazy? What's the matter with you?" Einstein tells him, "Oh, don't worry. There's a great big fluffy cushion at the bottom. It'll be fine. The important question is, do you feel any gravity?" And the fellow says, "No, I'm in free fall. I don't feel any gravity." So if you were to have several clocks nearby, gravity would not be messing up their synchronization, right? And the fellow says, "I suppose." Therefore, locally, you feel no effect due to gravity. We have gotten rid of gravity, at least locally, close to your location at any point during the fall. The laws of special relativity are back on the books. And the fellow says, "Well, I suppose that you're..." And then there's a thudding sound as he hits the cushion. So imagine we have a curved space-time. An individual has a world line that passes through point P. If the individual is freely falling, then locally, at places close to point P, he will feel no acceleration. He will think that he is in the land of special relativity. At point P, the person's time basis vector will be the 4 velocity. The person is then free to set up spatial coordinates in any way he likes, could use spherical coordinates, or could use Cartesian coordinates. If the latter, then locally, close to P, all of the rules of special relativity are back on the table again. I have to emphasize, though, this does not establish a global Minkowski coordinate system because as the individual travels along their path, at some other point, there will be a time basis vector for that point as well. And we already know that it doesn't even make any sense to talk about comparing that vector to that one unless I tell you the path, in which case it does. Even so, this vector need not be that vector. All calculations will be done with points that are close to the point of interest. Having done that, in the same way as usual, we can introduce the dot product of two vectors. In a locally flat coordinate system, I can do the ordinary dot product as we've done before. In Cartesian, the components of the metric are delta alpha beta. In Minkowski, the components are eta alpha beta. And then if you wanted to be really careful about this, you would say that the dot product of vectors u and v at P are the components of the general metric at P, components of u at P, components of v at P. I have to mention anyway, most people are not this careful, so it's easy to get confused if you're not watching what you're doing. We will define raising and lowering of indexes as usual. Even in our locally flat coordinate system, the coordinates may be curved. Even so, if my system is locally flat, everything we've ever said is back on the table. We will do covariant derivatives the usual way. If you use a locally flat coordinate system, there is a basis for the one forms, which corresponds to the usual basis. There is a basis vector set that corresponds to the usual basis vectors. Then the calculation for the Christoffel symbols are done exactly the same way. Following the same argument that we did in flat space, the equations for the geodesics are the same equation. So we are basically back in business again. In Newtonian physics, the force acting on an object in a conservative field is the negative of the gradient of the potential energy. For gravity, the potential energy is proportional to the mass of a test particle, so I'm going to write the force as the negative of the mass of the particle that we're looking at times the gradient of the potential function for the field. In Newtonian situations, I'll feel free to use a Cartesian XYZ coordinate system, and in Newtonian physics, time is absolute, so t is time. I find out that the acceleration in the x, y, and z directions are given by the negative of the partial derivatives of the potential function with respect to x, y, and z. Either on a curved surface or in a curved spacetime, the geodesics are given by the usual equation. I'm going to be using special relativity units where the speed of light is 1. I'm going to make various simplifying assumptions here. I'm going to assume that I use a coordinate system where the metric tensor is diagonal. That's not really an assumption. You can diagonalize any symmetric matrix. Also, I'm going to think of being in a situation where the metric is almost the metric of special relativity. The speeds of objects are small, meaning since I'm using c equal 1, speeds of spatial coordinates are very close to 0, and the metric doesn't depend on t. That is, if you fix your position and don't move, the value of the components of the metric tensor don't change at that location. The idea that the speeds are small say that only dt d tau is much different from 0. dt d tau will be approximately 1, but dx d tau, dy d tau, and dz d tau will be very close to 0. That means in the differential equation, only the alpha equals 0 and beta equals 0 terms will amount to anything. The geodesic equation simplifies tremendously. We need to go off and look at that Christoffel symbol. And when I say that Christoffel symbol, of course, I mean the four of them. This term is 0. It's a derivative of a metric tensor component with respect to t with respect to x0, which by assumption was 0. That's 0 as well. So under the assumptions as stated, the second derivative of x mu with respect to proper time will just be the negative of Christoffel mu 0, 0. So we'll look into that now. Because the components of the metric don't depend on time, on x0, this derivative and this one are automatically 0. In calculating the mu equals 0 component of this equation, since the metric is diagonal, the only term I'm going to get here that could conceivably be different from 0 would be when sigma was 0, but the derivatives of the metric with respect to the time coordinate themselves are 0, so the second derivative of t with respect to tau in this situation works out to be 0 to this degree of approximation. The second derivative of x1 with respect to tau, the second derivative of x with respect to tau, is 1/2 g1 sigma, g00 comma sigma. But again, the metric is diagonal, so only when sigma is 1 do you get anything interesting. G11 in both the upper and lower components is approximately 1, since I'm using Minkowski type coordinates. So the second derivative of x with respect to tau, to a good degree of accuracy, is 1/2 times the derivative with respect to x of g00. You can make exactly similar arguments for the second derivative of y and the second derivative of z. So to summarize, I have the second derivative of x, y, and z with respect to proper time written in terms of first partial derivatives of a constant times one of the components of the metric tensor. But on the other hand, think back to the Newtonian situation, thinking of t and tau as being more or less the same in our slow motion, nearly special relativity situation, versus what happens in Newtonian physics in a conservative force field. Your captain has turned on the alarm bells. Partial with respect to x of half of g00 is the same as partial with respect to x of negative of the potential. Partial with respect to y, 1/2 g00 is the partial with respect to y of the negative of the potential. 1/2 g00 differentiate with respect to z gives the same answer as derivative with respect to z of the negative of the potential. Obviously, there's a connection here. You can add a constant in these equations, so I'm going to do this. This says that 1/2 g00 in our approximation must be the negative of the potential of the field plus a constant. Since the field is supposed to differ from flat spacetime only by a little bit, g00 needs to very nearly equal eta 00, which is -1. This tells me that the constant 2 times c should be -1. Under all the simplifying assumptions we're making, g00, aside from some multiples and some constants added in, one of the components of the metric is basically the gravitational potential. I've slipped into standard textbook notation. Many textbooks call the potential of the field phi instead of u, so I meant to write -1 minus 2u, but no harm done. The important part is this. That has physics in it. It has potential energies of force fields. That's part of the gadget that lets us calculate dot products and things. This is purely geometrical. This is purely physical. Our physics is slowly becoming geometry. Now, of course, if you're not in this special case, if the field isn't weak, or objects move quickly, or you don't have a metric that's nearly special relativity, then this analysis is not complete, but it is suggestive. It suggests that these metric tensor components are going to basically more or less play the role of gravitational potentials in more general situations. This suggestion turns out to be right, so the other shoe is beginning to fall now. Why are we so intent on knowing about all of these things? Because they describe the gravitational field. There's more to it than this, but this is probably enough for now. I hope everybody has a good day. I'll talk to you again soon.